Unit 3, Day 2, Rational Functions, Horizontal Asymptotes, and Graphing Rational Functions. So we're going to first talk about our end behavior, which is comes from your horizontal asymptotes of your graph. So the end behavior of a rational function when the absolute value of x gets large. So let's go ahead and look at, let's say f of x right here equals a to the nth power over b to the nth power be a rational function whose numerator has a degree of n and denominator has a degree of d. The graph has at most one horizontal asymptote as follows. If the numerator degree is less than denominator degree, then there's a horizontal asymptote, which is the x-axis or y equals 0, or whatever the number is on the outside. Because remember, if you have a number on the outside of your function, you're moving your graph up or down that amount. The next one is when the numerator degree equals the denominator degree, then the horizontal asymptote is going to be the ratio of the leading coefficients. So in this case, it would be a over b. And if the numerator degree is greater than the denominator degree, then the horizontal asymptote is none. That means we have an other asymptote. And to find the other asymptotes, you are going to divide the two polynomials, and the answer of the polynomial is the asymptote that describes the end behavior of the graph. So for that, if the degree difference between the numerator and denominator is just 1, then it's going to be a slant or oblique asymptote. If it's 2, it's a parabolic asymptote. So for example, and we talked about end behavior last year as well. So we're looking at the highest power of x because that is what the ends of your graph are going to resemble when you're looking at those values. So in this case, if I look at this first equation, notice that the degree of the numerator is 2 and the degree of the denominator is 3. So that means that the numerator degree is less than denominator degree. And we said when that happens, then your horizontal asymptote is just going to be at 0 or the number on the outside. So there's nothing being added or subtracted to this fraction, so that's why it's just 0. And we learned about end behavior last year when we talked about polynomials and when we talked about rational function. And so this means in the long run, if we were to look at our graph values in the very large x values in the positive and negative direction, so that means as x approaches plus or minus infinity, your y values, or f of x, is in this case approaching your horizontal asymptote, which is 0. Which is a very cool thing to think that we can actually describe the end behavior of a function for very, very large values of x in both directions, numbers that are so large that you can't even really think about how large these numbers are. So looking at the next one for b, so if I look at the degree of the numerator is 2 over a degree of 2. So now the numerator degree equals the denominator degree, and we said when that happens, then your asymptote is going to be your ratio of your leading coefficients, which in this case is 3/2. So we have a horizontal asymptote at y equals 3/2, and that means my end behavior as x approaches plus or minus infinity, so as we get very large values of x in either direction, your y values are approaching 3/2. And for the next one, now we actually have an absolute value in our equation. And so remember, when you have an absolute value equation, when you're solving, you have two answers. You have the positive answer and the negative answer. So that means we actually have to look at two different things now if you have an absolute value. We have to look at both the positive and the negative. So remember, you drop your absolute value bars when you look at both sides. So we have 5x over the positive answer, which would just stay the same, 10x plus 2. And then we also have 5x over the negative of the absolute value, which would be negative 10x plus 2. So looking at this first one, again, for both of them actually, the degree of the numerator is the same. It's 1 over degree 1, which means that the numerator degree equals the denominator degree. So we're looking at our leading coefficients. So in this case, here it's 5 over 10, which is just 1/2. So we have a horizontal asymptote at y equals 5 over 10, which is 1/2. And for this one, if we distribute the negative, that means this would be negative 10x. So that means we have a horizontal asymptote at y equals negative 5/10 or negative 1/2. And my end behavior that means we have two different values we're looking at. So we would have to say, which way are we going? So for the positive direction, we're approaching 1/2. And for the negative direction, we're going to approach -1/2. So let's look at the graph to kind of see. So if I turn this on, I have 5x divided by the absolute value of 10x plus 2. So if we go ahead and look at the graph, I'm just going to do zoom 6 for a standard window, make it look a little better. And you can see as x approaches the positive infinity, it looks like our values are going to be approaching 1/2. So we can even go to our table and let's actually plug in very large values of x to see. So we're going to ask. So if I do that, so if let's put in 100 and see what happens. So if I put in 100, notice I have 0.499. If I put in 1,000, it's even closer. And if I put in 10,000, it's even closer. So that tells me as x approaches infinity, my y values, or you could say f of x, same thing, approach 1/2. And as x approaches negative infinity, our y values, or f of x, approaches -1/2. And you can again confirm by looking at the graph or plugging in very large values of x in the negative direction. And that confirms that we are approaching -1/2. So that would be for my end behavior of this function. So you just have to be very careful when you're working with absolute value that you do both the positive and negative answer. So looking at the next one, so the degree of the numerator is equal to 2 over degree of 3. And so in this case, the numerator degree is less than the denominator degree, which means, again, we're just looking at the outside value. So in this case, the outside value is just 0, and the numerator degree is less than denominator degree. So we have a horizontal asymptote of y equals 0. And that means that our end behavior is approaching as x goes to plus or minus infinity. Our y values are approaching 0. And then for this one over here, the degree of the numerator is 1 over degree 2. So if we have degree 1 over degree 2, remember we said it was the number on the outside. So this is degree 1 over degree 2. So your horizontal asymptote is going to be y equals 4. So let's actually make this into one fraction to see why that is. So remember when you're getting something as one fraction, you have to get a common denominator. So I would multiply this by x squared plus 1 over x squared plus 1. So when I do that, I have a common denominator. So I would just have to distribute this 4 to both these terms and then combine like terms. So that would be 4x squared. So in my numerator, I have 4x squared plus 4 and plus this x over here. So plus x plus 4 over my common denominator, which is x squared plus 1. So now you can see if we rewrite it as one fraction, then you can see the degree of the numerator and the denominator would be the same. And so in this case, it's still the leading coefficient, so still going to be 4 over 1. So that's another way you can even show that your horizontal asymptote is equal, y equals 4. And so that means the end behavior, as x approaches either positive or negative infinity, your y values, or f of x, approach, in this case, 4. And so looking at the next one, for this function, same thing. So the degree of the numerator is 2 over degree 1. So now my numerator degree is bigger than my denominator degree. And so remember when we said that happens, the horizontal asymptote, there is none. That means there's an other asymptote. So the question is, how do we find that other asymptote? And the way that you find the other asymptote is by either using long division or synthetic division. So if you don't remember how to do long division or synthetic division, I do have some videos on that. But just real quickly, so remember we can only use synthetic division if we're dividing by a linear binomial with a leading coefficient of 1, which we have right here. So we can go ahead and do synthetic division to find my, in this case, slant asymptote, because notice the degree of the numerator is 2 over 1, which means there's only a 1 degree difference. That's how I know it's going to be a slant asymptote. So remember when you're doing synthetic division, you find the 0 of what you're dividing by, which in this case would be x equals -5. And that's what goes in the synthetic division box. And then remember that your dividend has to be in standard form. If you're missing any 0 placeholders, which we are for x here, you have to put those in. And then for the synthetic division, you bring down the first term, and then you multiply. 1 times -5 is -5, and then remember that you're adding these terms together here. So 0 minus 5 would be -5, and -5 times -5 is 25. And then if we add -21 plus 25, we get 4. Remember that last number is always the remainder. And your remainder is always because the remainder is so small, it doesn't affect our end behavior of our graph. So we're only concerned with anything that's not a remainder. So in this case, we get y is equal to, we have to put our x's back in when we do our synthetic division. So this was degree 2. That means you start off with degree 1, so x minus 5. So that means we have a slant asymptote at y equals x minus 5. And then for our end behavior, it's slightly different. So the end behavior, you're going to think about this polynomial here. So this is a degree 1, which is odd. And remember, the leading coefficient is positive. And we learned last year when you have an odd positive graph, and you can even think about graphing this out. If you have y equals -5, so your y-intercept's -5, and your slope is 1, so it's going to go up like this. As your x values get large, your end behavior, that means it's going to go to positive infinity. And as you get large in the negative direction, it's going to go to negative infinity. So that means this end behavior, as x approaches infinity, your y values, or f of x, is approaching infinity. And as x approaches negative infinity, your y values are going to negative infinity. So for other asymptotes, you have to look at the degree of the polynomial, and you have to look at the leading coefficient to help you determine what your end behavior is going to be. So for this case, whenever you have other asymptotes, your end behavior is always going to be approaching either plus or minus infinity. So again, you use your asymptote to help you determine that. So now I've plugged this equation into my y equals just so you can all kind of get an idea of what the graph looks like. So if I hit graph, I know this is not a very good graph that I'm looking at because if I look here, my domain restriction is -5, which means because there's no factors that are going to cancel out, that tells me I have a vertical asymptote at x equals -5, and I should be able to see on both sides of my vertical asymptote a part of my graph, which I don't right now. That's what tells me my window is not a good window that I'm looking at. So I'm going to do x minimum of -20, and I'm going to do a y minimum of -20 as well, and see if that helps. So now here I can see both sides of where my vertical asymptote would be. And if I go ahead and put that slant asymptote in, which is x minus 5, I'm going to make it a little bit thicker line so that you guys can see it real well. So if I hit graph, you can see that the ends of your graph are going to be following this asymptote right here. And so that's what happens when you have a slant or other asymptote. So again, the ends of your graph in the long run. So even if I hit zoom out, just to show you. So we're going to just zoom out. So there's my graph. It's not even showing you the lines where the vertical asymptote would be right here because your graph actually does go up. It's just our calculator doesn't know how to graph it. But you can see in the long run, it looks like my graph is following this slant asymptote, which is pretty cool that we can determine that just by looking at the degree of the numerator versus the degree of the denominator, and in this case, using synthetic division. So for this next one, if we look, we can see that the degree of the numerator is 3. The degree of the denominator is 1. So again, the numerator degree is, in this case, bigger than the denominator degree, which means there is no horizontal asymptote. And so we can use long division or synthetic division to figure out the other asymptote. Since we're dividing by linear binomial, we can go ahead and use synthetic division. So the 0 of my denominator would be 1. And so in my synthetic division box goes 1, and then we have our coefficients here. It's in standard form. I'm not missing any 0 placeholders, so that's good. So I have 1. The next coefficient is 3, 1, 1. So 1 times 1 is 1, 3 plus 1 is 4, 4 times 1 is 4, 4 plus 1 gives me 5, 5 times 1 is 5, and 5 plus the 1 gives me 6. And so in this case, the 6 is my remainder. But again, that's so small in comparison that doesn't really do anything to your graph. So we're more just concerned with this part over here. So we have started off with a cubic polynomial. And so we're dividing by an x. So that means that this degree is 1 less. This is going to be our x squared. So y is equal to x squared plus 4x plus 5. So for this one, you notice that the degree difference, the degree of the numerator is 2 over 1, so the degree difference is 2. So that's why this is a parabolic asymptote. And so for this, to find the end behavior, we want to look at the degree and leading coefficient of our parabolic asymptote. So the degree of this is 2. The leading coefficient is 1, so positive 1, so it's positive. So when we have a degree 2 that's even, positive, and even positive, when you think about your quadratics, you know both ends are going to go up. So that means both ends are going to positive infinity in this case. So the end behavior I know is going to be as x goes to either positive or negative infinity, my y values, or f of x, doesn't matter which one you write, are approaching infinity. So I went ahead and plugged it into my y equals. I plugged in the equation that we were given, and I plugged in our parabolic asymptote just so you can see. So first we're going to look at a standard window, which is zoom 6. And so when I look at that, I know I'm not seeing the full graph right here because I don't see anything to the right of where this vertical asymptote is, because remember, vertical asymptotes are 0 of the denominator. So that means I probably should zoom out. So if I zoom out and hit enter, so now the first thing it's drawing is the first graph, and then it's going to draw their asymptote. So you can even see that little U part up there. So now right there, that's actually the end behavior of our graph. So in the long run, even though our graph, when we're in zoom 6, goes down because there's a vertical asymptote right there at x equals 1, notice that the ends of our graph are going up to infinity, which again is very cool that we can actually determine that. So I'm going to go back to zoom 6 to just show you that means that's why I knew I wasn't looking at full window, because we have this asymptote here, so this other part of the graph that goes up. So in the long run, our graph follows along this parabolic asymptote. So this is our end behavior, and this was our parabolic asymptote. And again, we got that by using our synthetic division. And of course, you can always do long division as well. And if you don't remember the long division, it is on my website as well for extra practice problem. So let's go ahead and look at analyzing our functions, and we'll do some practice graphs. So when you're analyzing this, we're going to follow each of these steps. So I'm just going to kind of do them as we go. The first thing I always like to do is factor the numerator and denominator completely. So if I look at this first problem here, the numerator and denominator don't factor any further. So the next easiest thing to do would be to find the domain of the function. So when you're finding the domain of the function, recall that you are looking at what makes the denominator 0. So in this case, if we set the denominator equal to 0, we get x is equal to 2. So that means my domain is all real numbers except for 2. So negative infinity to 2 and 2 to infinity. So because there's no common zeros between my numerator and denominator, that tells me that this 2 is a vertical asymptote because I can't simplify this. When I plug 2 in, it makes my denominator 0. So again, that's why that's a vertical asymptote. The degree of my numerator is a degree of 0 because there is no x over a degree of um, 1. And so since the degree 0 of degree 1, that tells me that I have a horizontal asymptote at y equals 0. And so there are no holes because we don't, again, have any common zeros between the numerator and denominator. My x-intercept, remember, are zeros when you set the equation equal to 0, so 0 is the numerator. So if I do that here, I get 0 equals 3 over x minus 2. So 0 times x minus 2 is 0. That's why it's 0 is the numerator. 0 does not equal 3, so there are actually no x-intercepts, so none. My y-intercept is when I plug 0 in for x, so I have 3 over 0 minus 2, which is going to be negative 3 halves. So 0 and negative 3 halves. For my end behavior, I know before I even graph it, as x approaches plus or minus infinity, my y values, or f of x, are going to be approaching my horizontal asymptote, which is 0. So before we write the range, we're going to go ahead and look at the graph. So on my graph, if I am graphing this out, I'm going to go ahead and put my asymptotes on my graph first. So I have a vertical asymptote at x equals 2. And then I have a horizontal asymptote at y equals 0. So I always like to put those on my graph first. And so at x equals 2, we want to figure out what is happening in our graph. So I don't have any, in this case, I don't have any x-intercepts, but I do have a y-intercept of 0, negative 3 halves. So that is going to be on my graph about right here. And that's nice because that actually helps me know that my graph has to be in this lower region, because you always have to have part of your graph to the left and to the right of a vertical asymptote. There's always something to the left and the right. And so now that I have this point, I already know that my graph is going to be in my lower region and has to follow my asymptotes. Could you pick points and plug them in to see that? Yes. We could also do the big little concept to kind of help us see this as well. So to the left of 2 would be 1.9. So if I think about plugging 1.9 into my original equation, which is 3 over x minus 2. So if I plug 1.9 in my denominator for x, 1.9 minus 2 gives me a negative number. So negative 0.1. So remember we said when we have a number over a very small number, it's a very large number. In this case, it's negative, so that's why it's going down to negative infinity. To the right side of 2 would be an x value of 2.1. If I plug that in for x, I would get 3 over 2.1 minus 2, which is a positive number. So I actually know that this part of my graph up here is going to be on this region. But again, if you don't know, if you actually need to plug a number in, so what's to the right of 2, 3, and you want to plug that in, you can, that's fine. So if I plug an x value of 3 into the equation, I have 3 over 3 minus 2, and so that would just give me 3 over 1. So when I plug in the points 3, I get 3 out. So if I plot 1, 2, 3, 1, 2, 1, 2, 3. So my graph was a little bit off, but again, we're just drawing a sketch of the graph. It doesn't have to be perfect with points plotted. We're using that big little concept to help us. But if it helps you to actually plug values in to see where and what regions you would be, that would be fine. And now that I have something graphed to the left and the right of my vertical asymptote, I know my graph is complete. And so my range is all real numbers except for we don't have any y values of 0, so negative infinity to 0 and 0 to infinity. Okay, so let's go ahead and take a look at the next graph, number 2. So looking at the next graph, again, the first thing you want to do is factor both your numerator and denominator. So let's go ahead and take a minute to do that. And so when I factor my denominator, I get 3x um, minus 2 and x plus 1. Sorry, 3x plus 1 and x minus 2. So now that I have my equation factored, I can see that my x minus 2's cancel out, so leave me with x plus 3 over 3x plus 1. So that's my simplified answer. So remember your vertical asymptotes, let's look at the domain first. So the 0 is the denominator. So what makes my denominator 0? So here, this one right here, if I set it equal to 0 and solve, I get 3x equals -1. So x is equal to -1/3. So I know that's one answer. And then right here, if my x value is 2, I also get 0. So my domain would be -infinity to -1/3, -1/3 to 2, and 2 to infinity. And then because that's 2, if I plug it into my simplified answer, it no longer makes my denominator 0. So when I plug that in, I get 2 plus 3 over 3 times 2 plus 1, which gives me 5 over 6 plus 1, so 7. So I have a whole that means at 2 and 5/7. And -1/3, if I plug that into my simplified answer, it still makes my denominator 0 because 3 times -1/3 would be -1 plus 1 is 0. So that means the -1/3 is a vertical asymptote. My degree of my numerator is a degree of 2 over degree 2, so my leading coefficient of my numerator is 1 over 3. So I have a horizontal asymptote at 1/3. My x-intercepts are, again, zeros of the numerator that are not zeros of the denominator. So then I cannot use where I have the whole, so that's not an x-intercept. But if I look at my simplified answer, if I set that numerator equal to 0 and solve, I have 0 equals x plus 3. So that means -3 is equal to x. That's my only x-intercept, so -3, 0. My y-intercept, I can again use my simplified answer to find. So I have 0 plus 3 over 3 times 0 plus 1, which gives me 3 over 1, so it's 3. So 0, 3. And my end behavior follows my horizontal asymptote. So as x approaches plus or minus infinity, my y values are approaching 1/3. So on my graph, if I go ahead and graph this out, I know that my graph has an asymptote for vertically at -1/3. So just draw it as best you can close to the line. And then I have a horizontal asymptote at y equals +1/3, which would be in here somewhere. So let's go ahead and then look at the graph. So for the graph, I have a hole at 2, 5/7. So 1, 2, and 5/7, about 0.7. So it would be somewhere in here, very close to asymptote. It's kind of hard to draw, so I'm just going to draw an open circle about right there. So below that's again 5/7 at about 0.71, but it's hard to draw on this graph with this marker that I'm using. So then I have my y-intercept is at 0, 3, so 1, 2, 3, so that's right here. And I have an x-intercept at -3, 0, so -1, 2, 3, 0 would be here. So this is really nice graph because I don't even have to really use the big little concept. I can already see that my first part of my graph is up here. And again, you always follow your asymptotes. And the second part of my graph, because of that x-intercept, I know is going to be on this lower region. But if you want to do the big little concept still, you can. So we know this is x is equal to -1/3. You would just need to pick stuff to the left and the right of -1/3, very close to -1/3, but not exactly equal to. And so my range in this case is slightly different because we don't have any values on our on our horizontal asymptote, or we also are missing that y value from the whole. So in this case, my range, I'm going to write it up here. I have -infinity to my horizontal asymptote, which is, we said 1/3, and then 1/3 to 5/7, and 5/7 to infinity. For these, I'm not really going to make you guys write out the range for them. I just wanted you to kind of get an idea for what it looked like for these graphs, but we won't really focus on that too much. So let's do one more problem. This will be our last one. So for this problem, again, the first thing you want to do, so I would practice, maybe try doing this one on your own, but the first thing you want to do is factor, of course. So if I factor this, we have this difference of two squares, so x plus 3 times x minus 3, and in my denominator, same thing, difference of two squares, so x plus 2 and x minus 2. Nothing from my numerator and denominator are going to cancel out, which means that both the numbers in my denominator are going to be vertical asymptotes. So what makes my denominator 0, 2, and -2? So we have negative infinity to -2, -2 to +2, and 2 to infinity. So that means both these values are vertical asymptotes. So we have 2 at plus or minus 2, or you can write them separately if you want. The degree of my numerator is a degree of 2 over a degree of 2. You always want to think about it, your polynomials in standard form. So if we were to distribute that 2, it's 2x squared over x squared minus 4. So your horizontal asymptote is going to be leading coefficient. So my leading coefficient would be 2 over 1. So y is equal to 2. My x-intercepts, remember, are zeros of the numerator. So if I solve the zeros of the numerator, I'm just going to do that down here. I have 0 equals x plus 3, and 0 is equal to x minus 3. So x is equal to -3 and 3. So my x-intercepts are -3, 0, and +3, 0. In this case, because I don't have any common factors between the numerator and denominator, there are no holes. My y-intercept, we plug 0 in for x and solve. So when I do that, I get 2 times 0 squared minus 9 over 0 squared minus 4. So in this case, 0 squared is 0, minus 9 is -9. So -9 times 2 is -18 over -4, which reduces into 9/2. So my y-intercept would be 0 and 9/2. And so let's go ahead and start to graph this out. So when I'm graphing this, we have our two vertical asymptotes at 2 and -2. And we also have an asymptote at y equals 2. And so let's go ahead and use the information we're given. So we have x-intercept at -1, 2, 3, and +3. And we also have a y-intercept of 0, 9/2, which is 4.5. So right there. And again, this is very nice because now I know where my graph is going to be, because remember, you should always have something to the left and to the right of your vertical asymptote. So in this case, we have 3 different regions we're concerned about. This region here, in the middle, and over here. But because of these x-intercepts and the y-intercept, we already know where our graph's going to go. So we're down here in this region for this part of my graph, and we're over here for this part. And again, you could do the big little concept if you want. Just if you already have your x-intercepts, you already know where you're going to be at. Now, this other region in the middle, I know that both of these parts of my graph have to go up. How do I know they both go up and don't cross over this asymptote here? Because we don't have any other x-intercepts, right? So if there are no other x-intercepts, we know our graph can't go back down, that both of these ends in the middle have to go up. And so the last thing to do is do our end behavior. So for our end behavior, we know that as x approaches plus or minus infinity, our y values are approaching our horizontal asymptote, which is at 2. So again, even though the middle of our graph both ends are going up right here, that's not telling the whole story. Remember that end behavior is as your X values get very large in the positive and the negative direction. And so that's going to conclude the notes for today, and then we'll finish up the other graphs in class tomorrow.